Even if you don't know what that specific AI model is or what data it has been trained on, you can still translate this numeric code into a numeric code that another AI model can understand. Hello everyone and welcome back. This is Elho. Would you believe it if I told you we could handle foreign languages freely without a dictionary or even an interpreter? Or would you believe it if evidence emerged suggesting that AI possesses consciousness? This could be interpreted in numerous ways, but there's currently a very hot paper circulating within the AI community. It's termed the Universal Zero Metric of Embeddings, revealing that Google's Gemini and OpenAI's GPT, having distinct training data and employing varying vector techniques to construct their large language models, possess the capability to translate between one another. So essentially, using the diverse range of raw data, which we call embedding data, that is utilized here, we can then comprehend what it signifies within a completely different AI model. Even though these are different text embeddings, the approach put forward in this paper indicates that they can be completely translated from one to another. Should this become a reality, the sensitive text data within the original AI model could become directly visible and accessible on a different platform, potentially leading to very serious and significant security concerns and issues. It's a somewhat complex topic, but when you extend this idea further, it strongly implies that even vastly different AI models ultimately possess a fundamental, shared, and truly universal structure. This particular aspect makes it quite fascinating to consider. Let's delve into this subject matter step by step and examine it more thoroughly. You're familiar with the renowned ancient Greek philosopher Plato often spoke about a world of forms, which he called ideals. So, if you look here, you find things like a princess or a horse, which are actual specific entities. However, if we view this from a level higher, we can see them as animals, or perhaps plants, as living beings. And if we ascend one step further, there's the concept of beauty. And at the very highest level, we have the idea of the good, which is a concept that is quite metaphysical. He proposed a hypothesis that all essential concepts of the world have a single archetype. This paper we're looking at today talks about something similar. This is pretty interesting. Do you see this? The Platonic representation hypothesis, this specific hypothesis, suggests the existence of a universal semantic structure. So why am I bringing this up? Because it appears that each AI model is learning and performing independently. However, in reality, it's hypothesized that there exists a common universal structure, suggesting that sufficiently large models, particularly image models, would inherently possess an identical underlying latent model. And they actually went ahead and demonstrated this empirically. Simply put, they're arguing that for us humans, whether you live in America, or in Europe, or in China, there could very well be a common map of thought that exists. Plato suggested that even though we perceive tangible objects such as keyboards or spoons, there exists a realm of perfect forms or ideas beyond our visible reality. Analogously, in the domain of artificial intelligence, it is hypothesized that distinct AI models, given sufficient sophistication, will converge upon a shared conceptual framework or map for comprehending the world around them. And indeed, in this paper, they actually discovered this shared cognitive map, terming this method back-to-back, and by employing it, they translated the expressions from other models to demonstrate their findings. At this stage, we need to understand the concept of embedding. When AI models, especially text models or image, document, and audio data come in, they go through a process called embedding. What this means is that a specific word, for example, in a sentence like "error did bicep exercises today," is broken down into a concept called tokens. We convert that word or sentence into special numeric codes, and that's expressed in vector form. So as you can see right here, each corresponding token is represented in a vector form expressed in that way. And while this example shows a 3D representation, models like OpenAI's GPT actually use vectors with more than 3,000 dimensions. For instance, the word apple is represented using specific coordinates, and the word apple also has a specific vector representation. So apple and apple would be positioned closer on this coordinate system. So in this realm of artificial intelligence, whether it's English or Arabic or Korean or Japanese or Chinese, these are not expressed as languages where you say, oh, this is Chinese, but rather everything is expressed purely as numbers. And you can understand that this is done through embedding. And the embedding models used by Google, OpenAI, and Entropy, well, they're all quite different from each other. Therefore, because each language used has a different form, the method of representing them identically with numbers varies. However, in this paper, despite the fact that there is no paired data, that is, this embedding model, translated as an apple by OpenAI, and the embedding method used by Gemini, are not explicitly mapped, and even without a translator or dictionary, the numeric embedding codes used by different AI models can still be translated. So these embedded data sets, these embedding models with various training data, or queries, like when we throw a prompt, it goes into the embedding model and becomes a vector embedding. So once they're represented as vectors, they get stored in a vector database. Commonly, when we talk about a vector database, or vector databases, it's because any text models or similar inputs aren't processed as text. Instead, they're converted and stored numerically. This means a space is needed to store these things represented as vectors, and this storage space, which is called a vector database, is essentially a database. A vector database serves the purpose of storing data in a manner that facilitates more efficient searching. However, this paper demonstrates demonstrates that even using only these numerical vector codes, it's possible to extract sensitive details contained within the original document, such as email content or other personal information. So the proposed technology is called back-to-back, but what does this back-to-back suggest? Simply put, you can think of it as a universal embedding translator. So there's a specific AI model that processes and understands text, which it then converts via embedding. So with these numeric codes, even if you don't know what specific AI model or what particular data it was trained on, you can actually translate these numeric codes that you see into numeric codes that another AI model can fully understand. Does that make sense to you? Now, if you look through the paper, it talks about this back-to-back method. It says that with just this back-to-back method, without any translator or interpreter, translation is possible. How is that possible? There's an assumption. Right at the beginning, I mentioned it. There must be a universal framework of thought, a common map of thinking. Even if the languages used are Korean, Japanese, Chinese, English, and so on, there must be something similar in the way humans think. Similar to Plato's notion of thick concepts, even though various AI models are trained on diverse datasets and generate distinct vector embeddings, the underlying premise is that with sufficient advancement, they will ultimately converge and interact on a common conceptual map. Therefore, within this back-to-back framework, as previously stated, they're proposing a modular architecture, which is somewhat complex to describe, including a space-specific adapter module and also a pass-through shared backbone network. For example, when we have a G2 summit or a high-level meeting where representatives from various different countries gather for an international conference, each representative speaks in their own native language. Without interpreters present, it would be quite difficult to effectively communicate. Now, if we all used a common language everyone could understand, like English, which is widely used now, so everyone just uses English, and each representative has a separate interpreter who translates their language into the common one, then they could converse smoothly. This is what the back-to-back structure is like. The adapter here is basically the interpreter. An interpreter exists in this space to do this translation. So because there's an interpreter to translate into their own language, this is how the architecture is set up. But just having the architecture doesn't mean it runs smoothly on its own. There are many issues, like translation. How do we handle that? Now, how do we train it? We'll train it smartly to make it seem real and ensure the meaning is clear. This is what is shown here. The first rule is adversarial loss. Essentially, this means the translated output should be as natural as possible, like a native speaker, without any indication it's a translation. It must be very natural. Next, there's something called reconstruction, which means that even after translating it and going back and forth, when it returns to its original embedding space, the difference between them should be minimal. If the translation is accurate, there should be virtually no difference. We also established that as a criterion. Then we have what's called cycle consistency, which means that even if it's converted to a different latent space, a common language in the latent space, and then converted back to the original model's numerical code, it should still be very similar to its original form. This second point is also similar in content. And finally, vector space preservation. Originally, within this model, there will be numerical codes, for example, for things like apples and pears. Since they're both categorized as fruits, they'll be close to each other in the vector space. Meanwhile, an apple and a computer will be far apart. So, even after translation, apples and pears should still be close, and apples and computers far apart. The system keeps learning while checking if it reflects this structure accurately. So, as the system continuously strives to fulfill these four rules concurrently, it autonomously identifies which numeric code pairs share the same meaning without us having to specify it individually. Therefore, the research paper shown in the initial figure pertains to this concept. It's talking about the numeric codes created by two different AI models looking at the same content. So you see all these connections, right? You can see that the red dots and green dots do not mix and stay clustered together separately. So since each model generates numeric codes in its own distinct manner, they're essentially unrelated. Comparing them is truly challenging. However, upon applying back-to-back, this is the outcome. If you observe carefully, you can notice the overlapping section right here. Surprisingly, even though the numeric codes are made by different models, they appear to follow a single rule and overlap perfectly. This means that even if different AI models use different vectors, they can now be compatible. It greatly expands the potential for data utilization, and it allows for direct translation while maintaining the original meaning. This should work across text and AI models, so while we're discussing text, it also opens up possibilities for integrating these models with images or multimedia. This diagram shows that you can translate email content using just numeric codes. For example, here we have encoder A and encoder B. Let's say an AI model A has stored some content like this. So, based on this, you write down the details in the body. Let's just say these are emails, and now you've embedded them and stored them right here. This is the translation of that. But this thing in the middle, this back-to-back, it's actually an unidentified number. From the perspective of this encoder B, these are different artificial intelligence models, but they are made understandable. Because assuming the structure is the same, we can estimate this number will likely be like this, then modify it appropriately, and provide this information to AI model B, enabling it to comprehend the data. So even if it's a different AI model, it can understand the content from AI model A by converting it. This has been demonstrated in actual use. Now, this diagram here shows in more detail how the back-to-back technology works. Let's say we have a document here labeled DIA. We don't know what that is. This encoder here doesn't know. Let's assume there's an embedding method created by a model called N-money. So when it embeds, it becomes something we don't really recognize like UAI. But by using back-to-back, this UAI gets transformed into a different form. It translates it automatically. So initially, this model doesn't even know what UAI is. It just has the outcome outcome that back-to-back delivers, and yet it's able to translate something based on that outcome. There's only one explanation for how this can be achieved. Despite how AI models are trained, see how they're roughly similar in shape, just different colors? We can see that the assumption that they possess similar structures actually holds true. So, utilizing back-to-back technology, we demonstrated the percentage of original email content that was leaked from the numerical email code. When we tested various models, such as Stella and GT, it was revealed that as much as 80% of the information could be leaked. This indicates a remarkably high rate of information leakage. In practice, looking at the email, the original was Inron, basing, front line, but it translated as NRON instead of Inron. Basing was translated to a concept similar to compliant to the public. The bottom part was translated as trades 43102, but it was referred to as future transaction, and John was translated as is. The following expense report was translated as the upcoming expense statement. Isn't it surprising how it translates this way? The models don't even know what they learned. So, it successfully interpreted a foreign language without a dictionary or word list. Really. Even when we translate with a dictionary or interpret, we cannot always find the exact matching words. In a way, it's a certain aspect of language, and it's quite amazing that it translated it exactly as it was. Without even knowing what the number codes were, it accurately translated it to understand another AI. This means there's absolutely no problem even with a completely new topic or speech style. What we refer to as embedding is ultimately whether it's English or Korean. From a human viewpoint, we differentiate them, but AI essentially perceives them as numerical values via embedding. That suggests that AI might potentially be able to understand things by corresponding them to numbers. So even if AI models have different number codes, there's actually a lot of hidden information in them. When you look at the translated number codes, from our perspective, they just look like numbers, but for AI, that's not the case. Isn't that fascinating? In the research papers, it accurately translates even highly specialized disease names like alveolar periostitis, a term I've genuinely never encountered before, and the meaning of such words. For us humans, this is entirely irrelevant. It means that even if humans don't understand, the LLM can independently comprehend and make judgments. Therefore, if we comprehend that AI models understand the world through embedded number vector representations, then it implies that AI's understanding of the world could potentially differ somewhat from our own human perspective. Even if all we see are endless strings of numbers, humans can't interpret them, but AI has a much higher likelihood of being capable of far more advanced thoughts. And this back-to-back learning process actually stems from unsupervised learning with data that has no definitive answers. Ultimately, this paper suggests that AI's way of understanding the meaning of text isn't simply about token or attention connections, as it is for us humans. Instead, it's through vector representations within an embedding space, which allows AI to understand things intrinsically, or so it seems, because even though they were done differently, the vector embedding rules still mapped correctly. So I thought this paper provides some insight into what we should consider more deeply when developing and using AI technology in the future, and I wanted to summarize it for you. This has been Error.